Good morning. So my name is Tarek Alkhrdaji, and presenting today collaboration between the American University in Dubai, Kansas State University, and Structural Technology. And the purpose of the research was to evaluate the performance of beam column joint when it comes to bending capacity. That was the main objective. And it's phase one or multiple phases that aim at evaluating different concepts for strengthening of beam column joints, mainly for bending and also for confinement and shear using externally applied FRP reinforcement. So I think Dr. Salakawi did a pretty good initial presentation on this similar topic, because some of what I'm talking about is related to some of the concept that he mentioned in his presentation. Although he was talking about GFRP, but structural performance is the same when it comes to lateral performance and ductility and resistance of the columns. So typically, we do a lot of strengthening with FRP, right? FRP is a mainstream technology, and we use it for strengthening whenever it's viable. There are many cases in which we still cannot utilize FRP because of its limitations. Sometimes it's bending strengthening, sometimes it's a limit on confinement or overall behavior. An example you see in here, this is an exterior column on a building that require increase in bending, and that increase in bending could not achieved initially with FRP because it exceeded the ACI limit for FRP strengthening. So at that time, the option defaulted to a conventional method that involved enlargement, where you drill into the column, extend the reinforcement to get continuity, dowel, and increase the size of the column. And by doing this, you increase the bending capacity of the column in both directions, although you're doing enlargement, for example, on one side, because you're increasing the effective depth of the section. So in bending, you will have higher resistance. And this application, as an example, was lateral load coming from wind, not from seismic. There's another case I remember when we worked with, and I come from the practice side of this business, in which we had a parking structure that, due to gravity load, require increase in bending capacity on the top of the column. And for bending in column due to gravity load, the tension would require on the outside. Because this is an exterior column, it was exposed, it was easy to put FRP bars on the outside of the column, running them continuously to provide bending capacity. But unfortunately, we always don't have this condition. And sometimes we have, T type of construction where you have beams and column intersecting in two directions, or sometimes you have beam in one direction, three directions, and four directions. If you get to see designs been done lately and recently, you see a lot of different engineers becoming an architect, becoming imaginative in the layout of beams and columns and structures. We don't see anymore the old construction where everything is set on a nice grid of beams and columns, right? And this is to accommodate the needs and smaller footprints for these structures. So part of that, we start using FRP wherever we have challenges, right? And we use FRP a lot for confinement. We have a good understanding of the FRP for confinement. We can use it to increase the ductility, and sometimes also as part of it, secondary, the strength of the beam column joint by doing the confinement, which is applicable to rectangular columns and to circular columns as well. The challenge is sometimes with achieving the bending capacity, because to achieve the bending capacity with external reinforcement at the joint, this reinforcement needs to be anchored, right? We know with the steel we can drill, like the concept presented in the first presentation, you can drill an epoxy in steel bars. Even with that, the option is most of the time is very hard. Because we know from actual application is that most of these beam column joints are loaded with reinforcement, top reinforcement, bottom reinforcement, and ties. Identifying a spot to put sometime a drill and get a nice clear path for it, whether steel or FRP, is not always that easy. So this is, again, as I mentioned, is going to be the presentation for the first phase of the research topic, and it's focused initially on trying to identify procedures and concepts for developing bending capacity and developing FRP reinforcement to increase the bending capacity as part of the big picture, which is improving the joint capacity with FRP reinforcement, which we have additional tests. Would be some of them that's been done that couldn't make it to this presentation in this paper, and some of them are still being planned to be done. And this research included the phase one, 3 beams, 1 control specimen, and 1 specimen strengthened with FRP fabric, and 1 specimen reinforced with FRP bars. And all the samples, of course, had the same amount of geometry, same amount of reinforcement, layout of reinforcement, geometry, and strength. So this is a typical layout, which is similar to the previous layouts that you've seen for testing. It's represent a beam column joint, The columns and the beams have similar dimension of 350 mm or millimeter time in one dimension and 300 millimeter in the other direction. Reinforced with 4 T16 or Phi16 vertical bars and ties that are T10 at 100 millimeters on center. So the objective was to see what is an easy way to do, initial objective was what is a detail that can work for strengthening without having to do too much drilling into the concrete. And the objective here, where you apply the lateral load to this column at the side, you're going to achieve the maximum bending at the base. So the first concept was to bring in FRP fabric on the two bending direction, main bending direction, apply it on the face of the column, and turn it into the underside of, let's say, the beam, right? It's reversed. And doing the same thing in the other direction. Of course, one of the main issues is that as soon as this will be in tension, this will peel, is not going to provide capacity, and there will be stress constration. To address that, the solution was to fill in the joint to approximately 50 mm radius with thickened epoxy to create smooth transition for the FRP and prevent stress constration, and place a complete wrapping dissection to hold the FRP, and also applying what we refer to as a U-wrap on the side to also anchor the FRP. And if you notice, the FRP was not really extended all the way to the bottom, because in reality, we're going to have some type of most of the time we have slabs, right? So this thickness where the FRP was stopped represent thickness of existing slabs. So this is one of the samples. The other samples, we're trying to achieve the external, the bending capacity with externally applied FRP bars. So these bars are not inside. This is actually placed into grooves on the surface of the element. And I know this is a relatively a unique condition where you have a construction, the beam column connection with beams only in two directions. And although you may think this is really not very common, but we see it very often where we have this type of construction where they have the beams in one direction and one-way slab in the other direction. So we encounter this every now and then. The other option that we don't have in here that we considered, but it's not included in this presentation, is FRP bars that are placed directly on the face that will be exposed to tension and compression force. In this case, you put the NSM bars on this face and you drill into the concrete and epoxy in. Again, we're trying to avoid as much of the drilling concept, see how much we can get out of these concept before we move to something more common that we do. And again, in this case, we have a little bit of confinement. Really, it's only one layer, not intended the FRP to provide confinement to the section, but also to prevent maybe localized failure. The only concern with this concept is the embedment of the NSM bars. From calculation, we can determine that the development length is approximately 600 millimeters for this size of bar. It's 12 mm bar. And they were only embedded less than that. I mean, less than 300. So we were not expecting to develop the full capacity of the FRP bar. So it's also another variable we're looking into, is how much you can achieve with this configuration. For all the specimens, the concrete strength, except for the last one, was a little close to 30. The last one came out a little bit heavier, when higher strength, 37 MPa. All specimen tested about approximately 8 months, strengthened and tested approximately 8 months after the initial construction. For the properties of the FRP, and again the FRP fabric, most of it was looking at the laminate properties, 1 millimeter in diameter with 1240 MPa in ultimate tensile strength, ultimate strain at failure close to 1.7 of the laminate again, and then the modulus of approximately, let's say, 74 GPa. For the FRP bars, all the bars were 12 millimeter diameter bars with ultimate strength of 2068. The elongation at break close to 1.6%, and then the modulus was 131 GPa. So these are common products that are available, nothing unique about them. Commercial product similar to these are available by different manufacturers. This is the setup. And again, you can see here it's a closed loop setup with a steel frame, and the load was applied laterally at the top of the column, while the whole system was pinned down and at the ends to prevent, of course, lateral movement of the test frame. This is a sample with the FRP fabric, and you see here this is the FRP fabric on the face, tension face, both tension and compression face, because it's going to be a cyclic loading, with the wrap around right at the top of what we refer the column. It's upside down, and then U-wrap on each side. And here you can see some of this thickened epoxy, which you can see better in some additional photos. This is a sample with the FRP bars, and again, the FRP bars were placed on the side, not directly to the tension face, but rather to the other face, but close to the tension zone to see how much they can contribute and help in this type of applications for increasing the capacity. The loading protocol, we started with the initial cycle of 0.05, then 0.1, then we increased at approximately 20.25% for each cycle, and each cycle was repeated 3 times up to failure of the specimens. And here you can see the first results for the first sample, which is a control sample, CSP1. And it's achieved an ultimate capacity of approximately, lateral load of approximately 40 kilonewton. And the drift was close to almost 2.5 to 2.8 for this samples. Compare this to the results of the one with the FRP sheets. Here you can see there's the increase with the FRP sheet did not provide significant increases, barely jumped in from 40 to 45 or so. And the reason because we start noticing debonding of the FRP and at the corner where there's constration. It started debonding, and because of strain constration, it fractured. So still, we got a little bit higher drift, but not significant. A little bit increasing capacity, not significant, but this technique proved to be not very effective in increasing the capacity or ductility of for bending. Notice this actually should show an animation, but showing here. This is one of the last loops, and you can see the energy dissipation in this. I highlighted this so I can compare to the next one with FRP bar to see the difference in these two samples. Here you can see the one with FRP bars. The FRP bars did improve the capacity approximately 60%. We went from 40 to a little bit above 60 kilonewton and improved the drift also slightly. So overall, it was some improvement in the bending capacity of the sample. You can see here, this is one of the loop from hysteresis loop. You can see that the shape, it's not as fat as the one with the FRP, is a little bit thinner, so it's a little bit less of energy dissipation with this concept compared to the FRP fabric. And the reason is that the FRP fabric was slipping and was failing gradually, so dissipating a little bit more energy compared to the concept or the beam with the FRP bars. So these initial results indicated to us that, okay, the concept of FRP sheets turned in on the inside corner is not going to provide a lot of capacity versus the bars may have a potential. However, we need to try other additional configuration, which we're testing right now. I can discuss them quickly as we go through the presentation. So this is a sample photo for the sample, the benchmark sample, and of course it's yielded at approximately, I think it was like 30 kilonewton or something like that. And after that, after a couple of rotations, you get a crushing of the concrete and failure of the sample. This is the sample with the FRP, and here's the location at the corner where the FRP fractured after a few cycles of loading, unloading. And here you can see the thickened epoxy at this location. So this corner was filled to, again, 50 mm diameter with thickened epoxy, and the idea is to provide a little bit of smoother transition for the FRP and delay a little bit debonding and see if that would help as a concept. This is the one with the FRP bar, and part of the failure is exactly what we were expecting. The FRP bar would have theoretically achieved even higher than 60 kilonewton, could have gone up almost to 80 kilonewton. However, the failure in the bar, you can see initial signs of slip and failure within the bar. Part of it that reduced the capacity. So anchorage and development line definitely play a role into the capacity of this sample with the NSM bars. Here, comparable of the generally the load drift ratio for the 3 samples. So you can see here's the benchmark sample, the dark line, and then you see the one with the FRP sheet. So we did not really help or delay a lot the yielding. You can see a little bit of improvement in the load, and overall the drift really increased a little bit, but not significant in these samples. Again, because we didn't have a lot of confinement, we're trying to focus on the bending more than the lateral deformation of the sample. And the curve, the top curve with the dashed line, it's represent the one with the FRP bars. You can see that we delayed yielding of this reinforcement because the FRP bar were more effective in sharing the load and delaying the yielding of the reinforcement, and we achieved higher capacity. But again, because of failure due to development length, it did not develop the full capacity, and therefore it stopped at only 60, a little bit above 60 kilonewton. I showed you the typical energy dissipation. And initially, we were thinking that maybe with the higher capacity, a little bit more drift, we can get higher dissipation. Well, the results showed the reverse, in which the higher dissipation came from the FRP fabric. And again, that's due to the gradual failure and slippage of the FRP that gives a little bit more dissipation in this case. So that is basically the first phase of this investigation program. Generally. Both techniques provided some improvement, though we clearly identified that the one with the FRP sheet is not the best. Turning on the side corner is not the best approach, and that FRP bar or anchored FRP would be a better approach to increase the bending capacity in columns. Again, the higher strength with the NSM bar could have achieved higher if there's a way to develop the bar. So in reality, if there's a slab that can, the FRP, after it's been put on the side, anchored into the slab, that could have been achieving a little bit higher capacity and give higher increase in bending. It's not possible in this case. The one with the fabric gave some more dissipation, but again, this was not the concept, and the amount of dissipation in general was not significant to a level that's really worth considering, but just this observation from the results. And this is basically the main conclusion I mentioned, which is turning on the inside corner. It's not really working very well. And the reason we wanted to test this thing is that industry, it's been used. We see it very often used. And we're always concerned with this. So the full-scale test proved our concern. It's turning inside corner. It's not appropriate for the FRP. One concept we're thinking is when you turn the inside corner is to put an anchor, the fiber anchor at 45 degrees. That's something we may still evaluate. But we still, even with that, it may not be as effective as anchoring the FRP directly into the beam member. And additional specimens have been tested, but we didn't get the chance to present it in here. And the idea is looking at different anchorage. Again, FRP bar going straight. One of them is putting FRP bar on the tension and compression face, putting the FRP anchors, what we refer to as spike anchor or fiber anchor, where you drill into the beam and epoxy in, and then splay the FRP on the sides, and then wrap it to provide bond. So this one concept. The other concept is to turn the FRP, again, on the side and put anchor maybe into the corner. And there's a similar program going on with us, a different location, to try to combine all this information and try to better understand what is a good way to do the strengthening. There's a program going on right now we have with the NC States, in which we're testing also some columns under just lateral load to this time understand the confinement effect of different level of RP. And this is just initial results I wanted to show you, although it's not part of the paper for this presentation, shows the significant improvement. This is only confinement. There is no bending reinforcement, so simply confining the joint. But you can see confining the joint by itself can provide good increase in the lateral capacity as well as drift. And that's because confining the concrete increases its capacity, and depend on the axial load ratio, you can get a significant increase in capacity or just minor increase in capacity. So this is a second part that's we're trying to work on. And you can see here, this is one photo show the significant improvement in ductility on column due to confinement. So this is one of the column that was strengthened with 2 layers of confinement. Didn't take too much to achieve significant improvement in capacity. So I think with that, I wrap up my presentation. If you have any questions, we're more than glad to answer.
Tarek and Hayder, it's actually a comment, and I want to commend you for doing a test where the near-surface mounted reinforcement is not necessarily on the tension face. Mm-hmm. It's so refreshing to see something different, and there can be advantages of locating that reinforcement on what would be the sides of a flexural member, in terms of maybe achieving a higher strain in the steel before you reach a limit state in the FRP. So we rarely see something like that, and I just wanted to point it out because I think it's interesting and it's different than what's the norm.
Right. Thank you, Rudy. And I have to mention that we do this in practice. In reality, we have all kind of limitation when you deal with existing structure. It's not always nice, and you have access to all four sides. And sometimes you have to use your knowledge of mechanics of material behavior. But sometimes we try to be conservative, and these tests can help us understand really is our approach makes sense or not. In this case, it worked well. The concept of put it in the tension side and account for it in the design where it's located, and the development-led issue, it was right on the money. Thank you.